Hello everyone, this is a presentation and report of our 209AS final project and presentation. The topic is communication cost reduction for federated learning. My name is Shenghui Xu and my teammates are Mingqian Zhong and Yuxuan Fan. Next slide, please. First, I'm going to briefly discuss the background of federated learning together with intuition and motivation. Then we will discuss our framework implementation of federated learning with 3 independent compression algorithms. Finally, we will discuss the experimental setup and design, as well as reporting the result. With the development of artificial intelligence and increasing concern on the privacy of user data and other digital assets, federated learning is proposed to realize learning without direct data sharing. Each client trains on its own data, and the central node helps aggregating the gradients and maintaining a global model. However, frequent communication results in high overhead and low efficiency, which we aim to solve in this very project.
Here I'm going to introduce our 3 types of conversion methods. First, we implemented fixed point quantization, which is a common technique used to compress neural network. And we use 16-bit fixed point with 14-bit fraction length as our quantization. And the detail can be seen in the pseudocode. Our second conversion method is low rank approximation. We will decompose a matrix using SVD. And so after SVD, we can get U, sigma, and V. And then we select only the singular vector which contains most information. And we set a threshold level that they will account for 99% of the information contained in the matrix. And our third compression method is sparse transformation. We will, given a tensor, if there are many values inside it is close to 0, and then we will set a threshold to find out those values and directly set them to 0. And so this is an approximate method. And after that, we can transform the original metric into the coordinate format provided by the PyTorch. And so by doing this, if the metric is really sparse, then the transformed matrix will be really small. And the detail can also see in this pseudocode.
And hello, I'm going to briefly discuss the system and experimental setup and design. And first, we can see that we should initialize the central node together with the client node. So we should allocate the data between the client nodes and to pick and initialize the deep learning model adopted. So first, we will generate a class distribution by the liquid process or human attribution, right? That is to tell the data distribution among the 10 classes and fetch the data to initialize the client. And in each run of training, the client will train on its private data and generate the gradient, which is compressed by the presented methods and send it to the center. After using average-based or other aggregation methods, the center would update the model to generate a new global model and distribute this new model to all the clients to override the old models.
We first prove the feasibility of our feature learning framework. To make it easier, we only generated one central server and 10 clients. And we manually distributed the miniset to each client. And each client will has contains one of the classes in minisets. As you can see, we manually set the distribution. And to make it simple, we also set the learning rate as 0.01 and 0.001 to evaluate the performance. We find that when the learning rate is 0 and 0.1, the performance will lead to the fast convergence. And we also try to update the model of the central server with the sum of the gradients from our clients, and we will get a better performance. After that, we apply the compression methods in our feature learning framework and evaluated the performance. We can see that it will significantly reduce the communication cost with an acceptable decrease in accuracy. We also change the distribution of the data set, and to be more specific, we randomly distribute the data set to each client. And we can see the performance is a bit different, and we found the different compression mode methods may have different performance according to the tensor during communication, which is related to the dataset distribution. So I think it's wise to choose a suitable compression method based on the application so that we can make a balance between communication cost and accuracy. That's all for our project.
And in this part, I'm going to introduce the structure of code and design to you. And in the main, in the main file, we will set the parameters through the parameter dictionary and further use that to conduct experiments with different settings. And the model part, we can switch to the model file. Yeah, and we can tell that in the model file of class named net is implemented, and two major functions, test and train single batch, are applied to the center and client server respectively. The test is used to verify the performance, and the train single batch is for a single client to generate a batch of gradients and forward that to the center node. So that is basically the network part design.
As for the compression method, we implement in this file. And first one is the quantization, which is basically same as the pseudocode. And for the low-rank approximation, we separate into two functions. The first one is turn to 2D function. We will have to transform any high-dimensional tensor into two-dimensional. And then we apply SVD as our low-rank approximation. And to reconstruct the original metric, we'll times the U times S times V, and then we will get the original matrix. And as for the sparse transformation, we also separate into several parts. The first part is zeroize. We'll find out the value close to 0 and use the threshold to set them all to 0. And sparse will transform the tensor into a sparse format and the coordinate format. And to reconstruct it, we just simply call the toDense function. So it will transform back to the original matrix. Okay. So now we are going to run our code. Okay, here you can see our parameter setting. There are 10 clients, and we will run for 1,000 epoch. And the range is 0.01. And we set the quantization true, the approximation false, and sparse transformation true. And these two methods cannot be used together because you will cause some, because you should only apply one compression measure in each round. And quantization can be used with these two together. That's fine. And so here now you can see that every 20 each push, you will report how many communication size is reduced and the accuracy of the current model. Okay, so the program is ended and the overall communication reduced size is this, and which is very significant. And the test accuracy is approximately 90%, and which is also very high. So that's all our demo. Thank you, everyone.
Yeah, and we would like to add that the reduced size is counted by the number of like 16-bit or 32-bit float numbers, right?
Yes, the communication reduced size is the difference between the original tensor's shape and the later tensor shape. So it's a difference between tensor shape.
Yeah, so we can tell that gigabytes of communication bandwidth has been saved with the adopted process, right?
Yes.
Yeah.
Yes.
So that's all for our final project, and thank you.